So welcome. Have you ever gone to see the third movie in a series and found that the people in your group who had never seen the previous two enjoyed it just as much as those who had seen the previous two? That's a trick. That's what I'm aiming for here. We took some polls just before we started here, before the camera started rolling, and it's close to 50-50, maybe 60-40, of people who use C++ as their primary language today and those who do not on the project you're working on today. There are also quite a few of you who have seen C++ in the past and have been amazed perhaps at how much it has changed. So this talk is intended to have something that each of you can use. We're going to focus on how C++ has changed with a view to how we can adopt C++, modern C++ in our existing C++ code bases without having to go reinvent the world. But even if you are very new to C++, maybe you've hardly had a chance to work with C++ before, this talk should be good for you. It should give you a nice overview of what modern C++ is, with accessible code examples. But if you are one of those people who have been using C++ for 10 years or more, and there are a few of you, at least in the room and probably online, I'm sure that there are a few slides where we're going to go deep in a few areas, and I think there you will find dollars to donuts that there is something you didn't know, or maybe didn't quite appreciate as much. Certainly, we're going to cover some things, say in C++ 11, that I learned after C++ 11 shipped, because there's a lot to do. But let's take a look at this survey, and again, in accord with the title of the talk, with a view to how do we adopt modern C++ in our existing code. So the first thing I want to do is cover this difference between sort of classic C++ that we might have done in the 1990s and 2000s to modern C++ code. We're going to talk about move semantics and some new vocabulary types that you can use pervasively, especially in interfaces. We're going to talk then about two major mindset issues. If I'm going to use C++ well and idiomatically and really realize its strengths, what do I need to know? How can I think about it? And this also applies to how we update our code incrementally over time. Because some of these things are classic, we just have new and simpler ways to express them now. And then finally, we're going to talk about pointers, because what would a C++ talk be like without pointers? But there's pointers, and then there's pointers. So we're going to have some fun there. But let's first start with the book that you should know, that you should recommend. If you are looking for a book that has in a couple of hundred pages what every modern C++ programmer should know, this is the book to recommend. The second edition is on its way to the publisher and should be out around July of this year. The first edition is great and highly to be recommended. And you might notice that the author is fairly well known in C++ circles. And if you don't recognize the name, he is Mr. C++, the guy who invented the language and is still involved with its evolution today and leading that fight. So it's going to be updated very soon for the current standard, which was shipped last year, C++ 17. And much of what we're going to say can be found in even more detail there, as well as additional topics. But let's talk about classic and modern C++. If you have seen C++ code that was written more than, say, 5-7 years ago, it probably looked a lot like the code on the left-hand side of the screen. There's all sorts of new and deletes, and there's some repetitiousness and boilerplate. And the most important thing that I can say about that code, especially in a talk on migrating and adopting modern C++, is we can do a lot of this better now. But that code works. It works now. It still is valid. It still works as well as ever. If it had pitfalls, those pitfalls are still there. But C++ has a great backward compatibility story. We hardly ever break backward compatibility. So that code that you wrote 20 more years ago still works today. But if you are updating it, if you're updating this function anyway, or you are writing new code, you might find that you can do the same in fewer lines with equal efficiency. This is not turning C++ into C#. This is simply letting us spell efficient C++ more conveniently, like in any modern language, with many of the features that you've probably enjoyed in other modern languages, like automatic type deduction for variables. Instead of raw pointers now, we can use shared pointers, and the factory make shared function that will allocate a heap object for you. And you notice I never say delete anywhere because it's reference counted for me automatically. You'll notice the for loop in the middle is a range-based for loop. So if I'm iterating over every element in a range, not only is it easier to spell, but that code is more robust and readable, which is a key thing, because you can just read it and without looking at the body of the loop, look by construction, know, oh, this visits every element in the range from first to last. So there's a lot to like here, and it avoids some of the pitfalls on the left-hand side, like exception safety, for example, and leaking things. A lot of that is automated for you. That does not mean that you should go and rewrite all the code on the left in the right style, unless you're touching that function anyway. You do not need to rebuild the world. The code on the left still works. But when you write new code or when you are modernizing code, this is the kind of thing that you can do tactically throughout your code base. So strong compatibility story. And remember, the code on the left is clean now, but and safe, just as fast as ever. As an example, picking another modern language, Python is a nice, clean, modern language. I could have picked several for this. The point here isn't to say, oh, look, language A, language B, look, it's competitive. No, the point is, you can write clean code in any modern language, and that includes modern C++. So if you look at the mean function in Python, you can write it pretty much line for line with the same meaning in C++ today. And there you'll notice some things that we used on the previous slide, like automatic type deduction for the return values. And some of you might realize that, oh, in Python, I wouldn't actually write that for loop. I would just use sum and length. And in the C++ standard library, we've often had that. We've had reduce and size. So yes, you can write that yourself. One of the new things I'm not going to talk about in detail, but that works today and is shipping today in Visual C++, that's new in C++ 17, is that STL algorithm on the right-hand side, reduce. How many of you are familiar with the reduce algorithm or have heard of it? Fair number. How many of you know that you can make that run in parallel now by just adding an extra parameter? Ah, one. Good. Now more of you do. And this can run on multiple cores if that's a very large data set on a wide machine. And of course, I can always wrap them in a function if I want to just have the same as the left-hand side, sum over length. But that gives you an idea of some of the power that's available, and it doesn't come at the cost of lots of manual management of things that people associate with C++. Now, don't worry. C++ has always had, as part of its ethos, not only zero overhead, but now when we make things convenient, we always allow you to open the hood and take control and do things by hand if you need to. You always have that ability. Unlike some other languages which prefer to keep that hood closed, you can always open the hood and take control over data layouts, over very finicky details of how data structures are organized. But you'll find that much of the time you don't need to, because the clean thing is also safe and fast and efficient by default, but you can always take control. Now let's talk about a couple of specific things that are part of really modern C++. Move semantics was probably the most important fundamental feature that was added to the language in C++ 11, which began the modern era. And there are also 4 important vocabulary types that were just added in last year's standard that are worth knowing about. So C++ has always been a value-based language. So we don't just put every object on the heap by itself and carry around pointers to them. We have values that are physically on the stack. Like every type is a value type by default. We can put values inside other values. And so it's a very value-based language. And what C++ 11 did is doubled down on that. Now, you have always been able to have things like an efficient set or a vector of widget objects. And we can make that quite efficient. But you never in the past, on the left-hand side, would have thought of returning one of those by value. In fact, we spent a lot of time teaching people don't do that. Why? Because you take a whole copy of the whole container, which could be a million widgets, then you throw away the original, and then maybe you make a copy again to return it to the caller. Well, that's silly. Why would you do that? So we say, no, just new it up on the heap and return a pointer to it, so we're taking control ourselves, and it's efficient. The good news is you get all that efficiency without having to do an extra heap allocation or have a raw pointer, because now we say, no, you know what, that thing we told you about don't return them by value, it's okay now. Just return by value. And the reason is C++ has not just now copy operations, which are a deep copy, say, of the whole state of the container in this example, but they have the idea of a move operation. I'm moving a potentially very hefty, expensive value from here to here. When you do a copy, you do a deep copy of everything, and so at the end of the copy, all the data that's under here is still there, and now a copy of it's under here. When you do a move, we simply usually copy a couple of pointers and say, no, I'm just going to own your data, and we leave this guy empty, which is perfectly fine if you're about to destroy that source object anyway, like in this example. So return by value is cheap for nearly all types now, including the standard containers. And so we can use efficient value semantics, but we still get the efficiency of reference types. So think of this as a major optimization and doubling down on C++'s commitment to value types. They're still as value-based as ever. You can still write base classes if you want, but we're still as much in the business of value types as ever, but now there's this efficiency. Now let's talk about 4 specific vocabulary types that you will find yourself using quite a bit. And in particular, the first 2 are ones that you will use frequently on interfaces. So these are new in C++ 17. How many of you, show of hands, how many of you have enjoyed using more than one incompatible string class? Laughter ensues. How many of you, just curious now, notice the cameras are not on you, your backs of your heads, so you're anonymous. How many of you have written one of those custom string classes? That's at least 20, 30 people. So we have all these string classes. People build them. There have been historical needs to do that kind of thing. But if you are writing a function that accepts a string as input, what do you have to do in classic C++? You make it a template, or you make it take a char star comma length, which is brittle. It's the C-style way. You can get the pointer and the length wrong. So that's the kind of thing that leads to buffer overflows and things like that. There's this new type called string view, and there are variations for, say, W-string view for wide characters, where you can write a non-template function. That function on the right-hand side is not a template, but it can accept any contiguous range of characters regardless of the string type that owns it. In fact, the string types that know about string view, or the ones that string view provides a constructor from, you can just pass the string directly without doing anything. Like if you have a standard W string, you can just pass f of s, and it will take a string view. Think of it as just a pointer length pair, but it's encapsulated. It's a pointer that knows its bounds, and you can use to iterate over it on a range-based for loop or whatever. You can just pass it. Now, if you do have in the second line a character pointer and a length, you can pass that. Now, notice this. In the old days, if you had written your function f to take a char star comma length or a w char t star comma length, what would you have written? F open paren s comma len close paren. But you'll notice here, you write exactly the same thing, but there are 2 additional characters. They are the brace characters. And this is part of a general modern C++ feature called uniform initialization. What in the second line those extra green braces mean, where I just basically take s comma len and put braces around them, it makes them a single parameter, and it says construct me an object to pass. Well, I didn't even say the type. I don't have to. I know what the type is of the parameter. I don't need to repeat myself. So because I'm calling f of w string view, and I pass as the single parameter a braced list of a couple of things, it says, oh, I know what you want me to do. You want me to convert that into, as the constructor arguments of a W string view. Okay. And I get the exact same call site as today, except I just put 2 braces. You'll find this to be convenient in many cases where now I'm invoking conversions explicitly, but without a lot of ceremony. I don't have to repeat the type. It's clean, and I still get the benefit that that f function can take a character array that's owned by any of these things. If you were in the C++ WinRT talk, you will notice the third line is a WinRT H string. That has an implicit conversion to WStringView because it knows about string view. So guess what? You can just say f of s without any decoration because it knows how to convert to a string view to give you a view of the characters in that string. The fourth example is Qt. How many of you use the Qt or Qt libraries and frameworks? So the example there does not compile yet, but is likely to compile on a release real soon now, likely with that spelling, to convert to a string view. Of course, you can still today use the pointer comma length, like the .data and .length version if you want. And for some of the other kinds of strings, again, you can just convert it to a null terminated pointer or ask for the pointer and the length in whichever way those strings happen to provide that information. And you can use all of them to call string view. And the nice thing about this is I did not have to write a template. Question? How about a vector of chars? Yes, you can do the same thing with a vector of char. Because, and this is the one thing you must remember, and therefore it is in a special color on the screen, because vector of char is not guaranteed to be null terminated. Neither is this. So do not take a string view and call .data and pass it to something that expects a null terminator. It will continue on doing the usual thing of partying through memory until it finds a random null. Not what you wanted. So just be aware, this is not a null terminated view. It's really a sequence of contiguous characters, and I'm agnostic about what string type happens to own it, and I can use those characters. So that's the first. The second, which you'll also use a lot on interfaces. You probably noticed with string view, you'll use that a lot as a parameter type, to come into a function, to pass data to a function. Optional you will use often as a parameter or even more popularly as a return type. And if you're familiar with nullable in other languages, this is very much like that. But it's applied to a value, not just as a pointer. It says, oh look, I have a create function here that returns an optional string, which means I can return a string object or nothing. That's not an empty string. I can still return an empty string. I could do that if I just return plain string. But if I return optional string, I can return any kind of string, including possibly empty, or nothing as a distinct value. And then I can test for it. In the main line, I call create, and I can say if result. So if, that's a shorthand for if the result is not empty, go ahead and use it. If I try to use the result and I didn't check first, it will do the check for me. But if I'm wrong, it will throw. So if you want to make sure your code doesn't throw an exception, do the first part of main there to check the result first. But you can always check, just try to dereference it, you access the value, and if it's not there, then you will get an exception. And then you can handle that as you want. And finally, sometimes you just want to say, I have an optional string, and I want to use its value, or just use this default value if it's empty. There's a function for that. Use results value or empty. And that's why that exists. If result is not empty, you'll get results value. If it is empty, you'll get quote empty quote as your string, or whatever you put there. There are other functions, but that gives you a flavor for how you would use it. And this can be very useful on functions that return a value that might or might not exist. And if you want to express that, this is a great way to do it in new code. A variant is something a bit different. You'll usually use this within function bodies, or as data that you store someplace. A variant is kind of like a union that knows its type. So if you use unions and you're scared because they're unsafe, this is the safe version of that. And what it says is, here I have a value which always contains a single value, except in very strange situations it can become empty, but that's not part of the main use of the feature. It's a value that always has exactly one value, but it can be any one of these fixed number of types, one at a time. So I can actually make a variant that could be an int or a double, and I initialize it from 42, and v now holds an int. But its static type is not int. Its static type is variant int double. Its dynamic type is int at this point of the code. So if I ask to get the int, that succeeds and prints 42. If I try to get a double out of it, it'll say, no, 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 I'm currently holding an int. That's a dynamic check it will throw, and you'll get a bad variant access. But then I can go and with the same variable that a few lines above was an int, assign it a double. And now V holds a double, and now I can actually get the double, and that's just fine, because that's what it's storing. So think of it as a safe union if you're familiar with unions. It stores a discriminant that remembers its type, but it's type safe. You get an exception if you do it wrong. And because it's part of the standard library, and this is a widely used type, we can expect implementations to be quite efficient in the way that they manage data. So you can expect implementations to not do dynamic heap access or heap allocations if you're not storing huge types. Very close to variant is any. So as soon as people say variant, one of the first questions is, what if I have a variant and I want just that behavior, a single value, but it could be a different type at different points in its lifetime, but I don't know the types in advance. It could be really any type. This is for any type. This is a library for truly dynamic types in C++ standard. So now I can say auto a equals any42, so now I've got an any variable that starts off life as an int. I can cast it to an int, and that works. If I cast it to a string, that would throw, and I can get the exception. But then later I can assign a string to it, and now it holds a string, and that works just fine. So if you want a fully dynamic type, use that.
So for variant in any, can custom types be a part of it, like my own classes? Just
So for variant in any, can user-defined types be in that mix? Absolutely. You can write your own type. And with very few restrictions, pretty much anything can be put in. In this particular example, we're using a standard string, but you could be your own string type or a vector or some other thing that you wrote. So that gives you an overview of a flavor for classic versus modern C++. The old still always works, but now we have new ways to express things in new code, or as we refresh old code. Move semantics, because we're still a value-based language, but it's efficient, and those vocabulary types. But now let's talk about two general concepts or techniques that have always been part of C++ and should continue to be. And I include this part of the talk especially because we often will find people who use C++ not as their primary language. They're more familiar with the idioms of another language. So these are things to be aware of if you want to write idiomatic C++ well. The first thing is that when you construct any resource, when you allocate any heap allocated resource or dynamic resource, pass it to the constructor of an object that's going to own it and whose destructor is going to automatically release it. If you do that, if you make sure every dynamically allocated resource is owned by an object whose destructor is going to release it, you are going to have a great time in C++. So that's why now instead of writing new, we tell people don't write new, write make unique. And we get a unique pointer, which is a smart pointer whose destructor will delete the heap object. And it's just as efficient as if you'd written new and delete by hand with a raw owning pointer. But now we have that owning object. P is now not just a dumb pointer, and we'll talk about smart pointers more in just a moment. And when you do that, and you have a myClass object that you call open file, and it owns the file, and its destructor will release it, now when you get to the end of that scope, you get automatic cleanup, and life is wonderful. In fact, if you have a class that contains an object by value, same thing happens. When the gadget is destroyed, as part of destroying the enclosing widget, it will destroy anything that it owns, and then the widget destructor will destroy everything that the widget owns, and these are connected automatically. So if you destroy the widget, it automatically calls the gadget destructor. And if you have ever wired up by hand in Java or C# those dispose methods to have an outer object that owns an inner object, and you wire up the outer dispose to call the inner dispose, how many of you have done that? That's automatic, just contained by value, and we wire that up for you in C++. That's the default. And similarly, if you put an object on the stack, as we saw on the previous slide, the idea is in C++, if I put an object somewhere, its lifetime is controlled by its enclosing scope, and that scope can be a function scope, it can be another class, another object scope, so that whatever the function scope or the outer object scope goes out of scope or is destroyed, we automatically clean up the things inside it. So we're expressing by construction who owns what, and you can make that very efficient and useful. Now, one thing about exceptions, many people are fine with using exceptions because they come from languages where that's pretty much the only way to report errors. Those of you who have been using C++ know that there are some places where there's still a debate about whether to use exceptions or error codes, and there are some valid reasons for that. This slide and the next tries to summarize how to do error handling in C++ as we have it today. The first thing is, know what a real recoverable error is. A recoverable error means the function you called could not achieve what it advertised. Its preconditions were met, but it could not achieve its success postconditions. Maybe some resource it needed wasn't available, or something else happened, or the data it was given was mangled and it couldn't parse it. Only in those cases report things as a recoverable error. And so once we've defined what a recoverable error is, then the advice is prefer to use exceptions. If you must say you're exposing a C API, you'll have to catch and convert that to an error code. But prefer to use exceptions because they're not ignored by default, they propagate automatically, they work great in constructors and operators, and they keep the normal control flow separate from the error handling catch control flow in the callers, and error codes don't do any of those things. So prefer to use exceptions for those reasons. Those of you who mostly use other languages will go, well, yeah, of course, we always do that. But sometimes we have to teach that in C++ because there's a heritage there, and there are sometimes reasons why error codes get used. But the main thing is, what's a recoverable error, and prefer to report them using exceptions. What is not a recoverable error is a precondition violation. If you are calling a function and you did not meet its preconditions, the function has no chance to do anything sensible. And the way you should always think about a precondition violation, and this is true in any language, this is a totally generic CSE thing, is if your caller violated one of your preconditions, it's not that you're going to become corrupt. It's your program is already corrupt. Something is nonsensical. It was not what the program was intended to be able to respond to automatically. Therefore, it is hopeless for the program to do anything sensible. For that kind of condition, don't think of that as a recoverable error, because it's not. Therefore, don't report it as an exception. Use contracts, which are coming hopefully soon to C++, but for now, assertions to report those to a human being at test time, because you want to make the developer aware that if you violated a precondition, it's a bug in the caller's code. The human developer has to go fix it. If you violate an assertion in your own code body, it means that you have a bug, and whoever owns that code body needs to go fix it. Let's spend the rest of our time talking about pointers, because this is an important area of C++. And it's one where the practice is most visibly different from classic to modern C++. In C++ 98, we have long been familiar with code like this, where a factory returns a raw pointer. We try to use them. We make sure that we explicitly delete our locally allocated objects. And all that red code now is mostly wrong. Now we tell people don't do that. And it wouldn't pass code review as new code. But remember, we have a great backward compatibility story. That code still compiles and runs as well as it ever did. But for new code, that should fail a code review, because we have an opportunity to do better in new code. In particular, the factory should, by default, unless you have a good reason otherwise, to return a unique pointer. I need to allocate a heap object and pass it back. That's exactly what unique pointer is good for. It expresses single ownership of a heap allocated value. And I should just be using local variables and not doing local news. And that helps to manage my exception safety. It automates resource cleanup. I don't need any deletes, and I don't have to worry about whether they fire if there's an exception. The code on the right will clean up even if there's an exception. You don't have to write the dispose pattern, if you're familiar with that from Java or from C#. That's automated for you. So when you're allocating a heap object, prefer make unique by default. And the other major make function like that to allocate an object is make shared. Use that one if and only if you know the object is going to be shared with more than one shared pointer, smart pointer pointing to it. You can always convert from unique to shared if you change your mind later. But if the object that you're allocating might actually only be used by one pointer at a time for the life of the program, use make unique to start with. You can always convert to shared pointer later if you need to. If you know it's going to be shared, use make shared, because then we can do an optimization for you. Basically, we can allocate the object and its reference counts in a single allocation and save you an allocation and give you some nice space savings too. Whatever you do, don't write delete. And that's the most important thing we have to learn. Now, having said that, when smart pointers came along, any new thing, especially a good thing, will first get overused. The number one pitfall of C++ smart pointers, and why a lot of people have helped them get the reputation of being slow, is they say, smart pointer good, I will use that everywhere. I will pass them by value, and we're going to talk about that on the next slide. But as function parameters and return values, raw pointers and references are just fine. Note the previous slide said to avoid owning raw pointers. And an owning raw pointer is easy to discover, identify. It's the one you have to call delete on. But a pointer to something that you got borrowed, you're just referring to somebody else's object, as long as you make sure its lifetime exceeds yours, but you don't have responsibility for deleting it, such as a function parameter, raw pointer or reference is just fine. So you'll notice that the classic and the new is identical on this slide because this guidance has not changed. And if you're using a unique pointer or a shared pointer, you simply dereference it to pass to a reference, or you call .get if you're passing it as a raw to a raw pointer parameter. These are nice and efficient. Raw pointers and references, they're just a machine word, they're bit copyable, doesn't get more efficient than that. So those are still fine. Now, there are times you want to pass a smart pointer, but only if you actually need to talk about the smart pointer, and I'll show examples. Now, here's one of those slides where even if you know C++ and modern C++ well, you might discover something new. So sometimes I hear people say, well, smart pointers, but raw pointers are so easy to use. They do derived to base conversions, pointers to non-const automatically promote to pointers to const. And I say, yep, so do smart pointers. Turns out they're kind of smart. But there's one thing that people sometimes say is like, okay, but I know that smart pointers can't do the following, because sometimes I don't want to have another pointer just to the whole object. Sometimes I want to point to just a component of the object, say the data object that's physically inside a node object. And my data structure has all these shared pointers to nodes. But I don't want to tell my caller about nodes. I just want to give them back a pointer to the data. So obviously I got to use a raw pointer there. And no, you don't. You write that last line of code. That last line of code is a trust me. But as long as you get that one line wrong, this is so sleek. What you're doing is you're saying, I have a pointer to a node. Make me a pointer to a shared pointer to data that shares the reference count of this pointer to node and has this raw pointer to a data. As soon as you construct that on the last line, you now have a shared pointer to data, and they both share the reference count, even though one is pointing inside to a nested object, and that is perfectly type safe. The caller can use it just fine. And later on, eventually, when the last smart pointer goes away, the object gets destroyed. Doesn't matter if it's the inner or the outer one, because they share the same reference count block, and they both know the full object's type and what destructor to call. So it doesn't matter which of those is the last to go away, the object will get correctly cleaned up. This is a very handy feature, and one that I discovered after we shipped the standard, because I needed it. And sometimes you learn about things not until you need them. The good news is that C++ is full of things that you don't have to know if you don't need them, but when you look for them, they are much more likely to be there, especially opening the hood and taking control like this, than in most languages, because that's something that C++ has always placed a priority on. But again, do not needlessly manipulate reference counted pointers. Now this applies to shared pointers, to COM pointers, to C++ WinRT objects which don't have PTR in their name, but behave like smart references that when you copy them do an increment decrement. If I'm writing a function and all I'm doing is using a widget, why on earth would I take a smart pointer to widget if I'm not using the smart pointer-ness? I'm only looking at the widget. All that does is it pessimizes me to say, oh, you can only call me with widgets that happen to be owned in this way, which is a distraction. Usually you shouldn't write that orange code. Worse is if people pass it by value, because then it does an extra increment decrement for you. And worse is if they do it in a loop by taking copies of smart pointers. Please don't do that. When people do this, smart pointers get a reputation for being slow, and it's not because they're inherently slow, it's because they're being asked to do needless work. But because it's common, I point it out. Now, is this a real-world thing? 2 examples. A few years ago, Andrei Alexandrescu pointed out to me that Facebook's RocksDB, they used to be passing shared pointers by value all the time, that thing we said don't do that. The simplest fix is just to pass them by reference, like the top left. That's the quickest mechanical fix you can make in your code, and really you should take out the smart pointer itself most of the time. But as long as you pass it by reference, you don't get the increment decrement, and some benchmarks went up 400% in query in database in the transactions per second, queries per second that they were performing. They were spending a fair amount of time on hitting those popular cache lines, incrementing and decrementing those reference counts. Now that was a few years ago. You might say, well, that couldn't be true anymore. Those of you who went to Kenny Kerr's talk, I don't think he mentioned this in the talk, but he had a C++ WinRT factory cache and noticed it was a bottleneck. And so he thought, oh, it's got to be that mutex lock, because we all know mutex lock throttle performance, because he was taking a mutex lock on the factory every time you access the factory. A profiler is a wonderful thing. When he profiled it, he realized it wasn't mutex lock at all. Sometimes we blame mutexes and malign them unfairly. He had an extra return a smart pointer by value or copy a smart pointer that wasn't even needed, and it was that increment decrement that was consuming more than 50% of the whole time spent in the function. Now, why? Because a smart pointer increment decrement has to be thread safe. Therefore, it is an atomic operation. Those are more expensive than ordinary plus, plus, minus, minus. Most of the time, you would have needed to do it anyway, and that's why they're just as efficient as what you would have written by hand. But when you do them needlessly, if you start using smart pointers and you notice your code getting slower, look for these patterns, dollars to donuts. That will be your problem, and you can fix it, because it's just the trap that's easy to fall into. So that's the number one performance problem with using smart pointers, and it's avoidable if we use them correctly. We don't ask for needless copies. Now let me talk about the number one correctness pitfall, and this is subtle. So most people remember that, okay, reference counted pointers don't do cycles, so you need a weak pointer or something in there to make sure you don't have a cyclic data structure, and they can remember that. But sometimes when we re-enter code, we go through deep call trees, which happens all the time now as we compose libraries and we have callbacks that call back, and so we're going deep into a call tree. We have to remember that if the object that we're passing down a pointer or reference to from way up here, we need to make sure that it lives long enough to be used by that whole call tree. And the pitfall is, if there is something deep down below, could be 10, 100 levels below, that could invalidate that object by modifying the smart pointer that owns it. So the way you deal with that is you make sure that the smart pointer that owns it isn't something that could be invalidated down here. Here's an example of what I mean. Let's say I have this global pointer, a shared pointer widget called otherp. In my function f, I take a widget reference, as we just said we should. Oh, let's give me a widget that I can do something with, and I call some other helper function g, and then I use my widget. The author of f did nothing wrong. Void g, oh, well, I decide I need to reset otherp to something. Do you see the problem? If it could ever be that inside function g, when I reset otherp, I might have taken away the last reference count to that, and if that widget happened to be the one that when I returned to my caller was the one passed to my caller f, I could have just destroyed that widget, which can happen if I do, for example, this call site. So this should not pass code review, and you might say, oh, that seems awfully subtle. But there's an easy way to spot this. Notice what I'm doing in that red code. I'm dereferencing, I'm getting a raw pointer reference to something owned by a smart pointer and passing it down to code that can see the smart pointer, and therefore it could possibly modify it. In this case, it's easy to see that. It's a global. But also if it's an alias local, if I'm also passing a pointer that they could follow to get to the smart pointer keeping the object alive, that's the pattern to look for. Instead, the fix is simple. Take a copy of this reference counted pointer. So you're taking now a copy, which I just told you don't do unless you need to. Here's one place you need to. I take one copy. I now have a local, and I call it pin because it's pinning a reference count to ensure this widget stays alive. And then I pass a raw pointer I get from the pin. This is perfectly safe and cannot possibly fail because that pin variable is not alias. There is no way that the implementation of F or anything it calls can know about that pin variable. It's not global. There's no pointer path going to it. It's purely local. And you might say, oh, but atomic, increment, decrement, oh, expensive. Good reaction, but does not apply here. Because notice, we're taking exactly one reference count bump that protects the entire call tree. And it's only on the place where we're converting from a smart pointer to a raw pointer. It's only on that conversion from a smart pointer to a raw pointer. We hold the pin, and that single reference count protects the entire million instruction call tree. And you'll never notice the pain. And it's correct. So just be aware of this. And the same thing happens if you say using the arrow operator to call a member function. Same thing. That's also a conversion to a raw pointer. We're getting a raw this pointer, so we can call the foo function. Just make sure that you take a pin, and so if you're converting from a smart pointer to a raw pointer, make sure you're converting from a local copy. Nothing bad can happen to you. And this happens in real-world code bases, too. On the left-hand side happened, for instance, on the Edge team, this is several years ago now, and they've long since fixed it, but they happen to own a JavaScript runtime. An implementation. So from their C++ code, they would pass a COM pointer to JavaScript, which would then come back into the C++ code through a callback, because that's what you do, and then come back out, and sometimes the pointers were null. Sometimes the objects had disappeared because of this reason. So you take the pin, and the problem can't happen. You do the right-hand thing, and it doesn't matter what the big call tree does. You don't have to inspect every one of those millions of lines of code. You know you've got a safe safe reference count nobody else can see, and it protects the whole call tree. So quick guide to passing smart pointers. If you have a factory, prefer returning a unique pointer, but in the second set, prefer returning a shared pointer. If you know it's going to be shared, you are giving ownership to the caller. If you are a sync function, you take a unique pointer by value. That means you're taking ownership away from the caller so that you're expressing I'm a sync, I'm a consumer of that widget. Reseat, take it by reference, and then you can swing that reference to make the unique pointer to point maybe to a different widget. So, and the same thing for shared pointers. These are how you should pass unique and shared pointers, but again, only if you really want to make a statement about ownership, because every single one of these is making a statement about the ownership. I'm retaining a reference count, I'm transferring a reference count, or something like that. So here's the summary of everything we just said. The reason I put this slide in, it's repetitive to everything I just said, but it puts it in one place because you can then print it out and put it on the cubicle wall of whoever you know most needs it. And sometimes we keep it ourselves because it's a handy reference to have. I'm told it makes a great mouse pad. So that's everything we're talking about. Please remember to complete your evaluations. And we have time for a couple of questions if anybody would like to ask anything about anything that we've covered. Yes, could you please use the mic?
Sure.
Just one.
So for it's not on.
No, it's not. I think it's on now. But go ahead. If it's not on, I'll repeat.
So for the string view, Some of the built-in types have automatic construction conversions for string view. Others don't. Is there any mechanism or plan to make that extensible, sort of like the stood hash, variants, where you can provide your own implementation of an automatic conversion, so you don't have to specify the explicit conversion code?
Yeah. So the question is, string view, some string types have conversions to it, some don't. Is there an extensibility point? Yes, there is. It's that conversion to string view. So for instance, Kenny, when he did his WinRT H string, it has a conversion operator W string view, which gives it an implicit conversion to a W string view. That's how you opt in. When I mentioned the Qt example, they decided to do it initially, well, they're still thinking about it. I reported this like 2 weeks ago, and they're still thinking about it, but it looks like they want to do at least that named conversion function, where I showed the tentative name from their bug report there. They're also considering making it an implicit conversion by making it operator W string, it's string view. If your string type is 30 years old or isn't updated, use the pointer length extraction functions, however they're spelled, and you can put braces around it, and you can make a string view out of them that way. The main thing to watch out is to make sure that you match the character type, because just plain string view is 8-bit characters. W string view is W char Ts, which is not necessarily everything 16-bit sized, because char 16T is not the same as W char T. There's also a U16 string view. So there's a couple of common variations, but mostly you need to match the character type, and then you can just refer to anybody's contiguous character data.
Hi. I usually program in C#, but also do C++. And one construct that I'm very used in C# is try catch finally. C++, I never saw finally. I would like to know the reason why it's not there.
So C# has try catch finally. Why doesn't C++ have finally? So one reason is because there's less need for it. It's proposed sometimes, but if you follow the advice to use RAII or have objects own resources, that whole dispose pattern? That's what finally is often used for. For instance, in Java, the #1 use until they had try with resources in like 10 years ago, but the #1 use of finally was finally dispose, the dispose pattern that you wrote by hand. That's the default in C++. You don't only have a short way to write it, you never write anything. It's white space, it just happens. Still, sometimes people ask for it, it's sometimes proposed, but it's unlikely that we'll see it. However, in one of the slides I did briefly mention at the bottom, GSL finally. There is a GSL, Guideline Support Library, from the C++ core guidelines that Bjarne and I edit and others. And you can find a type there. However, the guidance on that slide was use it as a last resort only. In a nutshell, what you should do is, if you don't have an RAI type, write one. If the author of the library didn't provide one, write one, because then you can use it everywhere, and everything just works. When you actually look at the uses of finally in the wild, when they've used GSL finally or others, I think there's some in Boost and Scope Guards, every time I've known those to be audited, like for instance Windows has one internally, when they audited the uses, over 50% were wrong. That may resonate with you if you debug Java code where the finallys were not right. And that's not to ding finally. Occasionally it's useful, so that's why you have GSL finally. But it's you're driving in manual. You're not driving in automatic. Therefore, you have responsibility to take care of things at a much finer grained level. And as you can see, C++ is evolving where automatic is much more common and just as fast as manual. So we're trying to reduce those things so you don't have to write it. One more.
Okay, so one of the things I noticed that other languages do better is package management. So you can do, and in C++, you always all these include files, libraries. That to me is the biggest problem in C++. Are there any plans to? Does C++ 17 solve any of those, or are there any plans to do that in the future?
So the question is, include files, headers, ugh, and package management, ugh. Every other, Rust has cargo, Python, you got pip and PyPy. Why doesn't C++ have that, and will it? So no, it's not in C++ 17, but both of those things are being actively addressed. So the first thing is to get rid of the need to have header files and also to have scalable builds. Look for the modules proposal, so Google or Bing or whatever your search engine of choice is for C++ modules. That is undergoing standardization as we speak, and some of it might be, we'll know more next month at our next meeting, might be in C++20, but that's certainly being worked on, and it's available in Visual C++ today in experimental mode, so that you don't need include headers nearly as much, and hopefully never in the future. Package management. That is helpful, but definitely not sufficient for package management. There is much work going on, so Conan and there are other package managers that are out there that are starting to get traction. The one that I know well is VC Package, which is shipped by Microsoft, and you might have noticed just a couple of weeks ago we announced it's now available cross-platform, so it works on Windows, Mac, and Linux, and you can also cross-compile on a Windows machine to do fully Linux things and use VC Package there. It has almost 1,000 packages now. And so that's actually, I think that's about 10 times more than the last time I looked at Conan. But we're seeing progress in that area. So between modules and package managers, probably in that order, C++ is also modernizing in that same way. Yeah. So thank you very much for coming. I hope you enjoy the rest of the conference. Thanks for coming to Build.